Okay, so for the first section of chapter 2 is all about solving equations graphically. Now, I mentioned a little bit about this before. You can technically graph any function you want, or you can actually solve an equation by graphing. All you got to do is plug in the left side in y1 and plug in the right side in y2 and see where they cross. That's one way. Another way is you can bring the left side to the right side and look at it, set it equal to 0 and look for its x-intercepts. That's another way. And then there's another really sneaky way. So I'm going to go through this now and talk about it. So this first one has a graph that, well, this first one, you have the absolute value of x squared minus 3x minus 5. So what I'm going to do is I'm going to go into y equals, and I'm going to clear out whatever I have in there, and I'm going to go ahead and put an absolute value. And so I'm going to go to math, and I'm going to go to number, and I'm going to punch in the absolute value. And so I'm going to go x squared minus 3x minus 5. And then in y2, I believe y2 is x cubed minus x. Oh, x cubed minus x minus 2. Okay, and then I'm going to hit graph. So I get a W-shaped thing, and then I get the cubic polynomial. Now I can see that these guys cross in exactly one spot. That's my solution. So I'm going to go to second, calc. I'm going to select option 5 for intersect. And first curve, oh, yeah, that looks good. And then second curve, I'm on my cubic. Yep, guess. I'm going to hit enter, and it spits out an answer of 2.22062928 and 6.730619. So not too hard. It's actually pretty easy. Okay, so let's take a look at another one. If we have this one, you need to just plug in the left side. So let's plug in the left side. Whoops, left side. Let's plug in the left side. We'll hit y equals. We can clear this out. We'll clear that one out. And so that is 0.1 x to the fourth minus 5, right? And then y2 is 0.1 x to the third power minus 0.1 x plus 12, right? So you hit graph on that, and we'll see what we got. So this one, well, it may graph. There may be intersections up top. So I'm going to make my window a little bit bigger in the Y. So let's make our Y max. Let's jump that up to 20 just to see what's going on. And let's see if we get our weird looking W. It makes the W. It looks like an absolute value with the hump in it because the cubic inside of it. So there's that. And it looks like we can see both of them. We know that this red one's going to be cubic and it's down up. So we have two intersections. So we're going to do this twice. So second, calculate. We go to intersection and move to the left over here a little bit and then hit enter. And then second curve, get closer over this way, enter. But now it says guess. This is where I move it over because there's two intersections. So it's going to spit that one out right there. Negative 3.40242 and 8.40144. Then I do it again, but this time I'm going to do it when it says first curve. I'm going to select, oh, that's good. And it says second curve, that's good. Now when it says guess, I'm going to move over. Gotta move over here a little bit so that way it knows that that's the one. If not, it will default to the other one. So let's do that. And bam, intersections 3.868845 and 17.403988. Okay, so that's pretty simple. This one, you got negative x to the fourth plus 2x squared equals x to the fifth plus 4. With that, I would actually do, instead of doing graph the left side, graph the right side, you could actually bring things over. So I'm going to bring the x, I'm going to rewrite it like this: x to the fifth plus x to the fourth minus 2x squared plus 4 equals 0. So I'm actually going to do that. And now what I'm going to do is I'm going to look at two things here. I'm going to look at, hit y equals, and you can do this a number of two ways. It's the x-intercept essentially, but I actually do it so it's still the intersection. I do this. I punch in x to the fifth plus x to the fourth. Now you can find the zeros is what it's called, but I actually just do it get real sneaky and just graph in y2 I put in the 0, so that way it's still finding the intersection, but it's technically the intercepts, the x intercepts with this function. So then in y2 I'm going to put in 0, and then I'm going to hit graph. Now since it's a fifth degree polynomial, I can have up to 5 intercepts. So there's 1, 2, oh, it looks like that's it. It looks like there's only one answer. So then all I do is the same thing. Second, calculate intersection, and just boom, boom, pow. And it just tells me that my answer is at negative 1.2779191, comma 0. That's my x-intercept. Right? Easy enough. Okay, you can probably do this one on your own. Let's get to something a little more technical. This guy right here, this one's kind of weird. Well, here's the thing. You can actually let's get rid of the zeros of this are going to be the same as if the radical wasn't there. So what you want to do is you want to square both sides. So then just punch this in as if you have the no radical there. All right, so punch it in like you have no radical. Punch it in like you have no radical. So what is that, -1? Okay, so you get y equals, and then you go x to the fourth power. So let's clear this out. So x to the fourth power minus 3x cubed plus 2x squared minus 1. Okay, and just forget about the radical for now because that changes the graph a little bit, but it will still give me all the things that I need. Alright, so it looks kind of goofy, but looks like we have 1, 2 solutions. So you can find those by doing the second trace intersection thing, right? Makes sense? Awesome. Okay. So you can do that on your own. We've already done a couple of them. That's how you approach that problem. This is actually pretty cool because this is something you've never seen. This is called what's called a rational function. Okay, and with rational functions, you have you can graph them the same way, but here's what's crazy about it. If I plug this in, okay, if I plug this into the calculator like I see it, all right, I'm going to go top part. I'm going to go 2. Let's just clear it out. Top part, I'm going to go parentheses 2x squared, big minus x, big minus 3, close the parentheses, divided by, all right, parentheses 8x squared minus 7x minus 4, and I close it, I'm going to get what's called a rational function. And it's going to look kind of goofy. All right, you're going to see there's going to be asymptotes and all kinds of weird stuff going on here. Yeah. All right, so you can see that there's asymptotes going on, and that y equals 0 is where it crosses. But if I take that out for a second, just so we can get a better look at it, here's the crazy part. With this rational function, the denominator, okay, the denominator, that 8x squared minus 7x minus 7x, that minus 4, that's the thing that creates the asymptotic behavior. So we really don't need to worry about that one. What we got to look at is the numerator. So let's go back and just graph just the numerator. So let's just take this out. Take that out, take that out, that. Take all that out. Not that. Not that. Let's do this. It's probably easier just to clear it out and punch it in, but whatever. All I have is time. All right, now if we look at, oh, we don't need it squared. Now if we look at that, whoop, what happened? Oh, syntax error. That's because I don't need that parentheses. Now it should work. All right, so when you do this, now it should just be a basic quadratic. Boom. All right, and where the zeros are, basically, whoop, basically, looks like -1 and a little bit past +1. And I can find that by doing the second intersection. You know, like if I have this in here as 0 and find them, I can do that real quick. So if I do that, I just go second, calculate the intersection. First curve, yep. Second curve, yep. I guess, okay. Gives me -1 comma 0, and then I do it again. (1.5 comma 0). So there's that. All right, pretty easy, right? Now, looking at a problem like this, this says this says, according to the data population of the U.S. Census Bureau, the approximate population Y in thousands of Baltimore, Maryland, and Austin, Texas is between 1970 and 2000 are given by these two functions, where X represents the number of years past 1970, and what year did the two cities have the same population. So what you would do with this is you would graph Baltimore, you graph Baltimore in your calculator, you graph Austin in your calculator, and you look to see where they meet, and you find that intersection. So go ahead and see if you can do that with your graphing calculator. All right. You might have to manipulate your window a little bit, mess with the zoom, but everything should work out just fine. So I hope this makes sense. I look forward to seeing you in class soon, and may the force be with you.